With connection to our previous algorithm, think about this question. This question has appeared multiple times in the code competitions. The question goes like this: as your input, you are given this two-dimensional array where 1 represents land and 0 represents water. So wherever you have a 0 here, it represents water, and wherever you have 1 here, it represents a land. And your aim is to determine the number of islands in this area. And what is island here? When you see two ones horizontal or two ones vertical, so this entire thing represents one island. So in this figure, the parts which are shown to you in this orange boundary, they are your islands. So since all these ones they are horizontal, vertical, then you have this one horizontal, this one vertical. These two are, and these are horizontal. So the thing makes up one island. You can also consider the diagonals here. So if you see here, these two ones, they are diagonals and they are also counted in the same island. So any ones which are horizontal, vertical or diagonally opposite to each other are counted in the same island. So how do you determine the number of islands? And your job is to determine how do you convert this problem into graphs. And can you see this problem as a problem which is related to finding the number of connected components in a graph? So I'm leaving it as a homework exercise. Think about it, and if any of you gets the solution for it, leave it in the comment box as I have described you in the email. Okay, next we are going to start with a slightly different topic. So how do you delete a vertex or an edge from a graph? Given to us, let's say a network on students in a classroom, and one student resigns from the institute. So in this friendship network of this classroom, probably I want to delete that particular student, and that is the same as deleting a vertex from a graph. So on the left hand side, there is this graph shown to you on 5 vertices, and on the right hand side, so what happens when you delete this C from the graph? So C is deleted along with all the edges which are incident on C. So CD, CE, CB, CA, all these 4 edges are deleted. C is also deleted from this network, and this is what remains. So that is how you delete a vertex from the graph. And how do you delete an edge from the graph? So assume that instead of deleting this vertex C from the graph, let's say C has some quarrel with this node E here, and both of these nodes here, they decide to break their friendship. So this edge CE is going to be deleted. What will be the new graph? So in this case, when you delete an edge, no vertex is deleted from the graph, only that particular edge is deleted. So this becomes your new graph. So there is no edge CE here. Other than that, all the vertices and all the edges are there in the graph. As an example, if you delete this edge BC from this graph, so what happens? Again, all the vertices are there, A, B, C, D, E, F. Only your edge BC is deleted. What sometimes happens, there are certain vertices which are responsible for connecting the graph. As an example, look at this vertex C here. What will happen if I delete this vertex? What will be the resultant graph? So when I delete this C here, I have A, B, D, which are forming a triangle with each other. C is deleted, so C goes away along with all of the edges incident on it, and what remains is E and F connected with an edge. So this graph gets split up into components. This graph is disconnected now. Similarly, what will happen if we delete B from this graph? Again, we'll be having two components, which will be, one will be A and D, B is deleted, another will be C, E and F. So sometimes when you delete a vertex from the graph, the entire graph can get split. It can become disconnected. And the same can happen when you delete an edge. So that's already happening here. If we delete this edge BC here, what is happening? This graph is getting disconnected and it's having two connected components now. So any such vertex which one deleted from the graph becomes disconnected. It is called a cut vertex. In this figure, which so do we have any cut vertices in this figure? Well, yes, we have. If we so vertex A is not a cut vertex. Why? If you delete this vertex A, what will be remaining is the edge AB and edge AD will go away. Vertex A will also go away. Still your graph remains connected because still you can reach from any vertex to any other vertex by a path, walk, trail, whatsoever. But what if you delete C from this graph? So as soon as you delete C, the edges CB and CD go away and the vertex C also goes away. What remains is A, B and D here, and C goes away and we have this E, F, G and H here, and the graph splits up in two parts. So the vertex C is a cut vertex here. Similarly, the vertex E is also a cut vertex here. It will result in a symmetrically opposite figure. Cut edge, again an edge whose deletion disconnects the graph. So in this particular graph, which is the cut edge? So as we can see, definitely this edge CE here is the cut edge. If we delete CE, the graph becomes disconnected in two components. Do we have any more cut edges other than CE? Actually, we do have. So AB is also a cut edge. What if you delete AB? So we have already discussed when we delete an edge, no vertex is deleted. So A still remains in the graph when you delete the edge AB. So what you have is A, B, and then this remaining graph is here in its original form, I think something like this. But if you look at this graph, it is actually disconnected. It has two components. One component is this one big component here and another component is this isolated vertex here. So AB is also a cut edge. Do you think there are any more cut edges in this figure? If you think yes, comment it on the classroom. Okay. Sometimes what happens, the deletion of a single edge doesn't make the graph disconnected, but if you delete more than one edge, the graph can become disconnected. So the set of these edges, which when deleted result in a disconnected graph, we call that set as cut set. So if you look at this figure here, let me label these vertices A, B, C, D, E. So there is no edge in this graph, which if deleted, the graph will become disconnected. But if you remove both of these edges, B, D and C, E, both of them, the graph will become disconnected, something like this. So we say that the cut set of this graph is nothing but BD and CE. So we now know the definition of cut vertex, cut edge and cut set. Let's look at a few aptitude questions based on these. So the first one, will cut vertices and cut edges always exist? And I think we have already answered that. We have seen that it is possible that they do not exist. So can you think of an example? So give me an example of a graph which has no cut vertex and an example of a graph which has no cut edge. That is, there is no way you can delete a vertex from this graph that the graph becomes disconnected. And again, whenever I'm asking you any question, you can always comment with the answer on the Google Classroom. If you have any doubt, again, you should type it on the Google Classroom. You all can discuss it with each other on Google Classroom. I'm also interacting with you there and I'll answer if none of you is able to answer a particular question. Okay. Next one. Is it possible that exactly one of them exists? Exactly one of either the cut vertex or a cut edge? So the question we are asking is, and Actually, questions 2, 3, and 4 are related. So also quickly read. Let's quickly read questions 3 and 4. So the question is, question 3 says if UV, if it is a cut edge, then do you think that U and V, these should be the cut vertices? Or either one of these should be the cut vertices or both of these should be the cut vertices. Similarly, if U is a cut vertex, then all these edges which are incident on U, do you think all of them are cut edges or at least one of them is a cut edge? Do we have any such condition? So for the first question, maybe I'll skip it. I have already given an answer here. So yes, it's not necessary. So here is an example of a graph in which you don't have a cut vertex or a cut edge. So feel free to give me some other graph as an example. Okay, let's look at here. So is it possible that a cut vertex exists in a graph, but there is no cut edge? Let's say this is a cut vertex and these are all the edges which are incident on this cut vertex. And do you think that all of these edges should be the cut edges or at least one of these should be the cut edges? As an example, let me take a star graph. I have a star graph here. So A is a cut vertex here. If I delete A, what will happen? I'll have 4 components and every component will consist of one node. Then I also know that AD is a cut edge here because if I delete this edge AD, I'll have 2 components, D and the remaining graph. Similarly, AB is also a cut edge, AE, AC. So I actually have cut edges here. And all these edges which are incident on A, all of them are cut edges. But is it true in every example? Do you think in any graph, all the edges which are incident on cut vertex, they are the cut edges or not? So let's look at a slightly different example. In this graph here, what is the cut vertex? I think we have only one cut vertex here, which is B. And we have 4 edges which are incident on B. And you see here, do you think they are the cut edges? BC. BC is not a cut edge because if I delete BC, the graph remains connected. Similarly, BA is also not a cut edge. BD is not a cut edge. BE is not a cut edge. Rather, none of these is a cut edge. We have a cut set. If we delete both BD and BE, or similarly, if we delete these both AB and CB, we have a cut set, but we do not have a cut edge. So it can so happen that we have a cut vertex in a graph, but there is no cut. Furthermore, there is no relationship between a vertex being a cut vertex and edges being the cut edges. Okay, can it happen that a cut edge exists in a graph, but there is no cut vertex? So here is, let's say AB cut edge in, so if AB, I'll show it like this. B is connected to some portion of the graph. So this is the graph at the side of B. This is the graph at the side of A. And definitely both of these, they are not connected in any way, because if they were connected, then AB wouldn't be a cut edge. The graph will not become disconnected if we remove AB. So there is no link between these otherwise disconnected portions. So this edge AB is responsible for connecting these two. If you delete AB, the graph becomes disconnected, right? So do you think A and B should? So definitely yes. If I delete A, then AB will be deleted. So delete A. So A will go away with all of its incident edges. So AB will definitely be deleted, and once it is deleted, the graph becomes disconnected. And same is the situation with B. If you delete B, AB will be deleted as a result of deleting B, and again this graph will be disconnected. It means that A and B both should be the cut vertices. So whenever we delete, if an edge is a cut edge, then both of these vertices, both of its endpoints are actually the cut vertices, with one exception. So it will hold for almost all the graphs, but there is just one exception to it. Can you think about that? Can you think about a graph in which when you delete this edge, actually none of its endpoints are the cut vertices? This happens in the case of pendant vertices. So look at this graph here. Here, if you look at this edge here, edge 3, 6, this edge is a cut edge. If you delete 3, 6, we'll have two components. This one over here will be one component, and this isolated vertex will be another component. But if you look at 6 in this case here is not a cut vertex. Why? Because when we delete 6, the vertex 6 go away, this edge will go away, and we'll have just this one component as the graph which is connected. So only in the case of pendant vertices this condition fail. Otherwise, if you have an edge, both of these vertices will be the cut vertices if they are not the pendant vertex. Okay, so this was all about cut vertices and cut edges. In the next part of this lecture, I'll discuss about Euler path and Euler graphs, which I think you have already studied on YouTube. Uh, I'll give you a different proof for the Euler graph, for the proof for the Euler graph and having all the even degree vertex in the graph. The proof which you have seen in the videos was through induction. The one I'm going to give you now will be by construction. So it's okay, whichever proof you find easy to follow, you can go with that one.